let's take a look at the ellipse in a little bit more detail. So far we know the ellipse, its eccentricity is less than 1. Here's a typical ellipse where the foci would be on the x-axis. I've labelled the two vertices there, A and A dash. The foci, well actually at this point I'll just put in one focus. We label S, same as we did with the parabola. There's my directrix, I'll call its x-intercept Z. Now, what we know is that the distance from any point to the focus is equal to the eccentricity times its distance to the directrix. So distance from S to A will be the eccentricity times distance from A to Z, but also the distance from S to A dash would be the eccentricity from the distance from A dash to Z. I mean, it doesn't matter which points I pick, that should be true. But I'll use those points because they're nice horizontal distances, so they're easy to work out. If I add them together, then we would get 2A, if you look at it. Right? Because SA dash plus SA is, well, the difference between A dash and A, that distance. So we can see that's 2A. If I was subtracting, then all I'm going to do there for the subtraction is sub in the values, EAZ and EA-Z. Okay. But if you also have a look at A-Z minus AZ, that also would be the distance between A dash, if you look at it closely. So distance from A dash to Z, take away the distance from A to Z, again I'm left with 2A. So I know that SA dash plus SA is 2A, SA dash minus SA is 2AE. Okay. I'm going to add them together. So I get 2 lots of SA dash would be 2A outside of 1 plus E. So SA dash is A outside of 1 plus E. Okay. If I was to subtract them, I get that the distance AS is A outside of 1 minus E. Okay. So our focus. I can now work out the coordinates because OS, the distance from O to S, would be the same as the distance from O to A minus the distance from A to S. And we've now worked out the distance from A to S. And it works out to be just AE. So that's nice and neat. So whatever the vertex is times the eccentricity, that'll get you the value of the focus. And as I say, they are in pairs. The shape is symmetric. So there's one over at AE, there must be another one over there at minus AE. Now the equation of the directrix, so we need to work out what Z is. So OZ will be OA plus AZ. Well, AZ, I'm going to rewrite the definition of the ellipse. If I rearrange it, I'll get SA divided by E. Because remember, SA will equal eccentricity times AZ. Subbing all that in, and then playing around with the fractions, we just get A divided by E. So it's quite nice. The focus is A times E, directrix A divided by E. And again, there would be a matching one over on the other side due to symmetry, so the other one would be minus A on E. Now the good news is obviously you don't have to derive that every single time, but let's come up with the actual equation of the ellipse itself. So we now know the focus has coordinates AE naught. There's my random point, XY. Need to work out the coordinates N. Well, we know the X value, because that's going to be the directrix. And because we're talking about a horizontal distance, the Y value will be the same as the Y value of P, so we'll just call it Y. So there it is, SP equals eccentricity Pn, subbing into our distance formula. Okay, square both sides, Y minus Y is obviously 0, so that bit disappears. It's still looking a bit messy. There we go. X squared on A squared plus Y squared on A squared 1 minus E squared is equal to 1. But we can do better than that. When X equals 0, we know Y is equal to plus or minus B. Well, if we sub that in, look what happens. B squared actually is equal to A squared 1 minus E squared. So the equation of the ellipse, if A is greater than B, so that means our ellipse is stretched along the x-axis. It's simply x squared on A squared plus y squared on B squared is equal to 1. We need to remember that. Well, B squared will be equal to A squared 1 minus E squared. The foci will be at plus or minus AE naught. The directrices, x equals plus or minus A on E. E is the eccentricity. I prefer to remember it this way. Much easier, I think, if you remember it as E squared is equal to A squared minus B squared over A squared. Okay? Now, we will always end up with a number less than 1 that way. So how do you remember it all? Well, it has to be A squared minus B squared. Because if it was B squared minus A squared, remember we've said A is bigger than B. So B squared minus A squared would end up being a negative number. And so E squared couldn't equal that. So it's A squared minus B squared, but then divided by the A squared. Some terminology there. We have a major semi-axis. So major meaning the big one. So that would be A for this one. The minor semi-axis would be B. Now in a circle we just have radii, but it doesn't matter where you go, they're all the same distance. So an ellipse, and obviously that distance is going to change. So the major is the biggest it could ever be, the minor is the smallest it could ever be. Now what would happen if B is greater than A, so it's the other way around, but now your ellipse is going to be stretched along the y-axis instead of stretched, and so it means the foci will be on the y-axis. So the foci is on the y-axis, so instead of B squared equaling A squared 1 minus E squared, it'll be the other way around. A squared will be B squared 1 minus E squared. The foci, instead of being A times E, will be B times E, and it'll be the y value instead of the x value. The directrices, instead of being A divided by E, it'll be B divided by E, and it's y equals. So you have a horizontal line instead of a vertical line. Area of an ellipse, just may as well put it there for the sake of completeness, is a formula that you actually know already. You might not have realised it, because it is just the area of a circle. But of course in a circle, the major axis is the same as the minor axis, so we'd say pi times r, pi r squared. So it's really the equation of the circle. Same idea. So we get pi AB. Okay. We're going to find the eccentricity of the foci, so all the basic stuff. We hope we get questions like this and we say thank you very much, some gift marks, but obviously it means we need to know these. Our reference sheet, there is not a separate extension to reference sheet, so you won't find all these definitions on a reference sheet. You're going to have to know them. There's our ellipse. X squared on 9 plus y squared on 5 is equal to 1. A squared is 9, so A is 3. I mean, those of you thinking, oh, but it's plus or minus 3. No, A is just a positive number for this. Okay. So I'll work out the eccentricity, A squared minus B squared on A squared. We end up with 4/9. Eccentricity of this one is 2/3. Foci plus or minus 2 naught. Directrices become plus or minus 9 on 2. Now we're going to draw it. And we're going to draw it using a wonderful method known as the auxiliary circle method. The auxiliary circle is the circle which has the same radius as the major axis. So there it is, radius 3. The ratio B on A becomes important. So in this case, √5 on 3. And we can just store that value in the calculator for what we want to do. Because what we do is we simply pick any vertical line. Now at this stage there's only one vertical line. And we can basically measure. Get a ruler, measure whatever that distance is, multiply it by the square root of 5 on 3, bang, that's where you plot your point. So let's assume, because the radius is 3, let's say I've drawn it 3 centimetres. So I'd go √5 on 3 times 3, I'd plot it at √5. But then I could draw any vertical line in and do the same thing. Measure it, times it by √5 on 3 and plot, and then because of symmetry I can plot the same below, but then also because of symmetry I can plot the same to the left. And then pick another vertical line, Same again. Symmetry, other side. Pick another vertical line. Measure it, root 5 on 3. Other side, do the same. I can pick another vertical line. Measure it, root 5 on 3. Other side, root 5 on 3. And you can see the ellipse is starting to form. There it is. Our lovely ellipse. So that's known as the auxiliary circle method. Would they ever ask you to draw it via the auxiliary circle method? Been years since I've seen a question like that. But it's a technique. Nah. Now you just get your template and go use the ellipse on that. Much easier. Okay, plot in the foci. Let's draw in the directrices. There they are. And we have a beautiful picture. Major axis for this one is 6. Notice I said major axis, so it's like diameter. Ooh. Make sure you read the question. Then whether they're asking for major semi-axis, so that would be like radius, or major axis. And the minor one would be 2 root 5. Okay, let's work out our equation here for this one. We've got to complete the square, but on the x squareds and the y squareds as well. Much preferred if the coefficient is 1. So if we divide everything by 36, I guess, 9 fours are 36, aren't they? So there we go. I'll get x squared plus 2x on 4, y squared minus 4y on 9, and then over the other side 11 on 36. Complete the square on the x squared plus 2x, we get x plus 1 all squared. On the y's, we'll get y minus 2 all squared, but that now means I have to add in a quarter for the x's and 4/9 for the y's. Something amazing happens. 11 on 36 plus 1 on 4 plus 4 on 9. Oh, that works out to be 1. Wasn't that lucky? Oh, that was quite good. Of course, if it didn't equal 1, then you would just divide it by whatever number it is and you'd make it 1. So it worked. We've got some shift happening, but the same as we would see with the circle. So the centre of this ellipse is at -1, 2. B score, notice, B bigger than A. So this one, the foci are going to be on the y-axis. So I'm interested in B squared here. So the eccentricity now will be B squared minus A squared on B squared, because we're going the other way. We get root 5 on 3, which means the foci, again, they've been shifted as well. So the x value will be -1 instead of 0, and we'll have B times E is root 5, but then that's been shifted up 2. So we get 2 plus or minus root 5. The directrices then would be B divided by E, but again shifted up 2, so we get 2 plus or minus 9 on root 5. Look, the reality is the ellipses that we're going to look at, they're going to be centred at the origin most of the time. Right? Again, very rare to have one that's not centred at the origin for these questions. So, Patel, remember that was the textbook. We got that somewhere.